So, you are totally justified in your head now of going, dang it, Dr. Clausen, we spent 3 chapters, and you didn't manage to get into any chemistry stuff at all. What the heck? That's atoms and elements today, isn't it? Chapter 4. Damn. That took you forever. Okay, so we're going to start off on elements. So elements are going to be pure substances from which all other things can be built. They cannot be broken down into simpler substances without losing all of the properties. No, you're good. You're good. Finish it up. Without losing all the properties that would make them that element, right? So if you go down past, you would get something that would not look like sulfur at all, which would not look like carbon, etc. Okay? Now, is everybody good with elements so far? Has everybody heard of elements before?
Yes.
No? Okay. Fantastic. Note that the periodic table has what on it? Elements. Okay, are these the same elements as water, wind, fire, and earth?
That's Avatar.
Funny enough, Avatar uses the Western element. Does anybody know the Chinese elements? It's the 5-element cycle.
Isn't it a dragon?
It has metal, no wind, and it has tree, living thing.
Yeah.
Yeah.
Is it iron? If they use the metal?
Gold.
Oh.
Gold is typically the pure metal. Yeah.
Okay.
But yeah, not that element either. So the element periodic table of elements, that is the elements we're talking about. Now the element names, these come from a variety of different sources, basically everything that you can want to name things after. Mythological figures, planets, minerals, colors, geographic locations, famous people, etc. Okay? Those were the major ones. These are some of the more interesting ones right here, and what they were named after. Maybe have some questions about that so far? No. There is a Tennessean, and this is Tennessee is named after. Anybody know why we would have an element named after Tennessee? Yeah, there's a really, really good lab that does nuclear chemistry, right? Anybody know the name of it? There's an old-timey band that's named after it. Oak Ridge Boys, Oak Ridge, right? Yeah. Nobody knows Oak Ridge?
Yes.
National Lab? Okay. Thank goodness. I'm actually pleasantly surprised. Oak Ridge, the lab, is actually more famous than the Oak Ridge Boys, apparently, which is awesome. So, chemical symbols. These are 1 or 2 letter abbreviations. Can you ever have a 3-letter chemical symbol? No, not normally. If you see a 3-letter chemical symbol, typically that's because they haven't finished naming it. Okay? And so they've given it a temporary designator. Okay. So when a chemical symbol contains 2 letters, the second letter will not be capitalized. For example, we have here cobalt, which is CO. The second letter is a lowercase o. This is very important because if you were to put 2 capital letters next to each other, CO, that would actually tell you you have carbon and oxygen. This is called carbon monoxide. Okay, so right now we have steel that has a little bit of cobalt in it all around us. If we had carbon monoxide all around us, would we be okay? No. So saying those 2 different things to a person has very, very different meaning, right? You're surrounded by cobalt. You're surrounded by carbon monoxide. Oh God, I'm going to die. Run away. Okay? Very, very different meaning, right? And so again, these are some of the 1-letter and 2-letter symbols that you can see here. Anybody have any questions about that?
So, like, when you give us the test, are you going to give us, like, their symbols or their, like, names?
I will give you a mixture of those things. Yeah. So I will tell you the names, I will tell you the symbols, I will give you a variety of mixture. I don't expect you to actually memorize it, but what I do expect you to be able to work it out. Okay? There is a periodic table, and so you can work it from the periodic table. Funny enough, I actually teach in one classroom that does not have a periodic table. I'm going to have to figure that one out. Probably put the periodic table up on the projector, I guess. We'll see. Okay, it's a weird thing. Chemistry professor, no periodic table.
Feels wrong.
Yeah, it does. It is wrong. All right, so again, these are some of the names and symbols of the common elements. Note that most of these symbols actually match the names quite well. Al, aluminum, right? Makes a lot of sense. Ar, argon. However, there are some that do not match the name. So iron, for example, Fe. And that's actually named after ferrum. And a lot of those actually have to do with the fact that a lot of this chemistry was done before English-speaking peoples were particularly well educated. And so a lot of the chemistry was done in French, German, and most of these people couldn't really say, hey, I want to name things in French, I want to name things in German, blah, blah, blah. They got into arguments a lot. And so they're finally like, we'll just name everything in Greek and Latin. We all know Greek and Latin because at the time that was the mark of education, right? And so, for example, we call this gold because we're English speaking. It is Au for its symbol. This comes from the Latin, which is aurum. That's the Latin for gold. And so aurum Au. Okay? Note that if you were to have a periodic table from somewhere that is not English speaking, they very well could put gold as whatever it is in their language. Okay? But the symbol would stay Au, and that's derived from Latin. Okay? Silver, that's Ag. This is from argentum. You all may have actually heard Latin with argentum in them. It's actually a fairly common, there's a saying essentially that if you accept the silver, you have to follow through. Yeah. And it actually uses argentum in that saying. So anyways, plicker. So please go ahead and get your plickers. If for whatever reason you do not bring your plicker, one way that you can get around that is you can take any large screen that happens to be nearby you. You can open the PDF that's located on Canvas, and then you could actually show that plicker, your plicker, on your screen. It will pick those up. Theoretically, your phone could also work.
Is it?
I won't be able, no, probably not, because it has one on the back side. That would have been the lab. Yeah. So remember, if you have lab with me, you also have a plicker for lab. And I had asked you to please put the designator that's for the lab on the back. Okay.
Dr. Vincent, I have 2 questions.
Mhm.
Periodic table.
Sure.
Why is 57 through 103 taken out?
Oh, because it won't fit on a paper. It would be about twice the length.
Okay. And aren't the ones that are like white with the black outline, aren't those man-made?
Yes. Yeah, they do not occur on Earth naturally. They could actually occur in space naturally, theoretically. There's certain spots. Mm-hmm.
This 118 was just whatever you and I. They hadn't named 118 when I graduated high school.
Yeah. Oh yeah. Yeah.
It was like 2016 they named it.
Yeah. Yeah. So I'll talk about it in just a bit. But the group that does this, if you get a bunch of PhDs and doctors,
I appear to have lost my clicker. Can I
that's
get it?
okay. So what you should do is you have a tablet there.
Yeah.
Go on to Canvas. If you go onto the Canvas for the lecture, there's a copy of your plickers. There's also a roster that you can figure out which plicker's yours.
Hold on.
Okay.
Hold on.
Well, you don't need, here. Anyways, we're gonna start the question, and then you work through getting the plicker card PDF. Yeah, there's a grouping of the PDFs. Okay. You'll need your number for this lecture. So you'll have to look your name up on the Plicker roster.
39.
And then you're going to have to go into that Plickers 1 through 63. See that?
Figure 1 through 63, yes.
And you're going to have to look up that 39 and show that. Okay? Don't forget to make it so your screen doesn't flip. Because if it flips, then you'll answer wrong. Okay. Okay. So right here we have the chemical symbol for iodine, iron, magnesium, zinc, and lithium. Which one of these is correct? That's funny. Okay. Okay, folks. Oh, your fingers are blocking, I think. Yep, you got it. Okay. Okay, and you can look up there and see if I got you. The people near the windows, by the way, the backlight from the window, please try to angle it a bit. Thank you. Yeah, the backlight feels it by going through. Okay. Anybody seeing yourself not get captured up there? Okay. All right, and so the correct answer is C. You got it. Okay. Notice that it had that iron again, which is Fe is the correct symbol for, rather than IR. Yeah. That was one of the big ones. Also, the zinc, it's Zn instead of Zi. Okay. Okay. All right. We'll do the next one as well. Okay, give the names of the elements with the following symbols. We have P, Ar, Mn, Be, and K for the symbols. So which one of these has the correct element? There you go. I think your hand is good. You got it. There we go. I think we got you there. Okay.
I didn't get the
Okay. Okay. There you go. Okay. Very good. Okay. And that is B. Yeah, and you'll notice that I actually didn't even put elements for a number of these. Like, that's an amino acid you can take as a health supplement. And this one right here, again, I have an arginine, the amino acid you can take as a health supplement. That's not an element, that's a compound, which we'll get to in a bit. And these ones are sort of the ones that are most tricky, but it has, down here, krypton. Which is actually an element. Mm-hmm. But it's way, way down on the periodic table, so it's named way after. Okay? Yeah. Mm-hmm. Potassium is K. And that's because P was used up, right? Phosphorus.
Yeah, phosphorus.
Yeah.
I was thinking silicon, sulfur, phosphorus, chlorine, argon, potassium, calcium.
Okay, so the next thing we're going to do here is right here we have mercury. That's Hg. This is a silvery, shiny element that is a liquid at room temperature. Mercury can enter the body through a variety of different pathways. The most dangerous pathways are going to be inhaling mercury vapor. The other most dangerous pathway would be ingesting mercury that has been concentrated in your food. Like example, fish, and the fish gets eaten, and then if you were to eat like dolphin or something, it would be quite dangerous. Okay? The other ways you can actually get a bit of mercury in you are contact with the skin. It does absorb through the skin a little bit. and just general ingestion or water that's contaminated with mercury. That would be incredibly difficult to do, actually. The old-time thermometers with the mercury in them did not actually leach mercury out.
Really?
No, you'd have to break them. Yeah.
I thought they stopped selling them for that.
No, they stopped doing them because the cleanup costs were so high. Because if you spill mercury, you don't want it to stay there because it can actually be dangerous if any heat hits it. Like it would roll into a radiator or something and people would breathe it. Yeah. And that, it's actually dangerous being breathed. Like it actually is very dangerous being breathed. Okay, does anybody know what famous character has mercury poisoning? Anybody ever heard of Alice in Wonderland?
Yes.
Yeah.
Everybody ever heard of the Mad Hatter?
Yes.
Okay, Alice in Wonderland is a commentary on the Victorian society. Victorian society, they wore the fancy hats, right? Yeah?
And I may be wrong about this, but wasn't the Hatter or maybe a different character supposed to represent someone undergoing the effects of mercury poisoning?
Yes, that's what I'm talking about right now. So the Mad Hatter was poisoned with mercury because at the time when you made the hats to get that stiff velvet, you'd actually have to use a mercury compound to do it. And so they would breathe in mercury while they're working on the hats, and the hatters, after doing that for years, would end up having mercury poisoning. And so some of the side effects of mercury poisoning is in the body, the mercury is going to destroy your proteins, it'll disrupt your cell function, and long-term exposure to mercury is going to cause brain and kidney damage. That's what you're seeing with the Hatter. He actually has brain damage. Okay? So he doesn't actually see stuff per se. That's just Alice in Wonderland in general.
It's all just
Yeah. It causes, technically this is not the correct wording anymore, but medically this is the correct wording, okay? Mental retardation, i.e. retardation of the functions of your mentality. This can decrease physical development as well. And this is why women that are pregnant normally will avoid things like tuna and stuff, right? Because they have a higher chance of having mercury in them. Fetuses are much more susceptible to mercury poisoning. Okay? And it can cause these effects much easier with a much lower dose on fetuses. Okay? So, side note, the Mad Hatter, he has his problems with rage and stuff, because part of this is it damages your nervous system and it makes you clumsy. So you're more likely to spill things, you hit stuff over. Your career of choice, the hatting, you can't do that anymore because you're too clumsy and you shake. And so that's why he's no longer a hatter in that, and he can't actually make hats. Is because he no longer has the dexterity to do it. And he's always like fumbling and breaking glassware and stuff. That's why. That's his mercury poisoning and his clumsiness from it. And then he has rage control issues because of his damage to his brain. Yeah, he's actually an incredibly tragic figure, isn't he? Mm-hmm. He seems so much less funny. Yeah.
he's just slowly dying of poison.
Yeah. Yep. He has been poisoned due to people's vanity. No joke. That's exactly his character. Yeah. So yeah, mercury poisoning, Hatter. Mm-hmm.
Okay. I realize it's probably going to be different for everybody, and that Hatter's probably an extremely exaggerated and sanitized example, but do most people who go through mercury poisoning usually end up acting at least somewhat like the Hatter?
I would say it was a fairly common, he's supposed to be a stereotype of hatters during Victorian era. So it would have been a pretty common, medium ground. Maybe there's no single person that does that, but his symptoms would have been exhibited in many different hatters.
Hatters sounded like they would have been really fun people to be around once you ignored all the dead by mercury poisoning thing.
Yeah, well, I mean, he was raging out at people all the time. So, temporarily, he probably would have been really fun to be around.
Yeah.
But, long term, he probably would have been really difficult, right? Because he's
Like a
reaching out at you.
like a sitcom character. Like you'd imagine they'd be great to hang around for a little bit, but if they were in real life and genuinely acting like that always, how long would it take before you put a bullet in them?
Yep, that was the Mad Hatter. So anyways, if you guys wondering if this is a modern day thing, it very much is. Anybody ever heard of artisanal gold? So it's where people extract gold using non-factories, i.e. over a campfire. What they do is they actually use mercury to leach the gold out of the ore, and then they separate the mercury and the gold over a fire, and they end up breathing in a lot of mercury vapor. Also, anybody ever wonder why the hydroelectricity has been something that like went away? Like Three Gorges Dam happened, then everybody's like, we're not going to do hydroelectricity much anymore. Mercury, yeah. So when you flood the plains to build up water pressure for your dam, you actually contaminate the water with mercury. And over the long term, it will leach out, and then you won't have any issues anymore over like 30 years. So old dams are fine, but that's 30 years of poisoning your population downstream. So, yeah. That's why that's kind of went to the side and people started ignoring it. Yeah. So this is the periodic table right here. Your periodic table is going to organize, as of the publication of this book, 118 elements into groups with similar properties and places in order of increasing atomic mass. They actually just discovered another element this year. Okay? So this book does have old information in it, but does that really matter for you? Probably not. Like, I don't think most people's lives are going to change based on a new element being discovered. This is what the periodic table looks like overall. You will notice there's groups, and we'll talk about those in just a bit. So in 1869, Dmitri Mendeleev created the periodic table. Dmitri Mendeleev actually arranged the elements by increasing atomic masses. Does anybody know what the modern periodic table is arranged by? Atomic number. Yeah, and we'll talk about atomic number in just a bit, but it's different than the atomic masses. Okay? And there's a good reason why we switched that over. So he arranged the elements into groups with similar properties, and this is really Dmitri Mendeleev's claim to fame. Honestly speaking, there were other people that also proposed a periodic table in the same time period. Okay, Dmitri Mendeleev is probably the most interesting character. So if you're going to read a biography or watch a biography, seriously look him up. He's kind of nuts. He's really something to see. But the cool thing he did is he arranged these into groups, and we can actually see even our modern day periodic table has some groups, doesn't it? Everybody see that? Okay, and so on his periodic table, the important part is he actually predicted the existence of germanium. And they found germanium a few years later, and it was almost exactly what he said. Very, very close. Excellent predictions. Okay? And he called it exa silica, i.e. it's below silicon. Yeah. Okay, now you had asked me before, this periodic table, why does this end right here? See how it jumps from 57 up to 72? Okay, so what's going on here is this entire block here fits in that space above. So the periodic table really should have this entire thing moved over. Okay? Now, they don't do that because our normal viewing platform is like this, right? And so if we do that very wide deal, it becomes very difficult to see, right? Also, your book is shaped like this, so they want to print it on pages that are printed in your book nicely, right? Anybody know how they used to get around this back in the day? They would actually give you fold out periodic tables. And so you take a page and it would actually fold out of your book. Yeah. And so then they could have the full periodic table exactly as it's meant to be. Okay? If you want to see one nowadays, you basically have to go on the internet, and you can find them on the internet just fine. but they're quite easy to get, and it will have the full one folded out, full length. Okay. Unfortunately, that just is not something that they provide you any physical media to look at anymore. You can buy posters with it, though, if you want, or print them off. You'll need the legal pages, though. So on the periodic table, the elements are going to be arranged according to similar properties in vertical columns. These are called the groups. The periods are going to be the horizontal rows of elements. These are counted from the top to the bottom, and they are periods 1 through 7. Theoretically, there will be a period 8 if we keep things up and we keep making new elements. Okay? In case you're wondering. We're actually getting pretty close. Right? So, actually, this next one that just was invented may have done that.
Yeah, because 118 is the bar.
Yeah. So, now that I think about it. Yeah, should have done that. So, technically, I guess there's a period 8 now. Yeah. Cool. So, periods 2 and 3 each contain 8 elements on them. Period 1 contains only 2 elements. That's hydrogen and helium. Anybody know what percentage of the solar system is accounted for on period 1?
81.
It's like 70-something percent, depending on what exactly you include. But anybody want to try to guess for period 2?
The solar system?
Mm-hmm.
6.
So period 2 is once you go period 1 and 2 combined, that's about 90% of the solar system. Okay? And part of that is the sun is primarily made of hydrogen, and then helium's a far distant second. And so the sun weighs far more than any of the planets, right? Yeah. But this is why, if you look at these elements here, carbon, nitrogen, oxygen, those are the major elements of life, aren't they? Yeah. And then this period 3 and below, they're that remaining like 9% or so of the solar system. So they're actually quite small amounts in comparison. Okay. So the group numbers, these are going to identify the vertical columns of your periodic table. They're written in 2 different ways typically. You have the letter A. This is used for the representative elements of 1A through 8A. And you can actually see that. That is not on that periodic table. That is on this periodic table. Can everybody see it okay? 1A, 2A, 3A. Okay. Now notice the other way of doing this is to just number them. And that numbering off has 10 additional elements in it, 10 additional spots across, which is the transition elements. That's that middle block right here. Okay. On some periodic tables, these will be designated with a B. Okay. All right. Now, these are the different groups and how they're arranged. And so here we have the alkali metals, that's group 1A. We have the alkaline earth metals, this is 2A. If you ever heard of earth metals, that's probably what you've heard. Okay. Transition elements are these ones here in the gray. These 3A through 6A, they don't really have common names. If you're going to talk about them as a group, you typically just use the first element on the top, okay? Or the most famous element in them. And people will get what you're talking about. Like, I'll say, you know, the carbons group. And then you look in carbon and you go down, right? Or, you know, the group with silicon in it. Okay? The next group, 7A, this is the halogens. And 8A is the noble gases. Does anybody know why they're noble? Yeah, they don't interact, right? They don't react. Yeah. You got it. They have full valence shell, so they don't interact. You got it. So the representative elements of each group are these ones right here. These are going to be called the alkali metals, and that's these elements right here. You are probably never going to see francium, since that one is actually never existed for more than like half a second. It's extremely reactive and radioactive. So, here's the alkaline earth metals, and you may see a number of these that are like important supplements and stuff, or can cause radiation in your body. Strontium. Did you guys know that bananas make you a little radioactive? Yeah. Yeah. Okay, and so group 3A, 4A, 5A, 6A, these don't really have super common namings. They don't typically talk about them there. These are the halogens right here, and then these are the noble gases right there. Okay, so this is the alkali metals. One of the most important things, and one of the things that people typically remember, is these are the metals that if you throw them into water, they're going to burst into flames. Okay? And so, for example, if you take lithium and you expose it to water, anybody know what happens? Yeah, it bursts into flames, right? Anybody know what happens if you charge your lithium batteries when they're really, really cold or really, really hot? So what happens is they actually make lithium metal in the battery. This will swell the battery and break the containment around it, in which case water and air will get to it, and they will light on fire. And if it's a really, really big one, like a solar panel farm or a one that's on a Tesla, it'll actually blow the vehicle up. And you can see those online on YouTube, Tesla's exploding during winter. Because they're really popular in Canada. And Canada can get really cold. You can avoid those issues by simply not charging it when it's freezing cold. Well, fair enough. I mean, there is kind of laws that are being talked about being put in place to make that not an option. So, but yes. But same thing with your lithium battery in your phone, by the way. That's why, like, those Samsung phones back, 5-7 years ago, something like that, started catching on fire. Is because if you use too many amps when it's too hot, you can swell the battery, and then the battery will break and catch on fire. Yeah. By the way, if you look at the packaging for lithium-ion batteries, they always have a packaging thing that says flammable. Yeah, and it typically has like a picture of somebody with a knife stabbing into the package, trying to open it, and it like breaking the battery packaging and lighting on fire. And the person going, ah! Yeah. So anyways, the sodium metal, this doesn't usually light on fire, but it does produce steam. It produces hydrogen gas. You can light it on fire if you try. Okay? Once we get back down here, though, we definitely light on fire really nicely. Okay? Lithium would not normally light on fire, but lithium batteries can get them so concentrated when you plate it out that it can start lighting on fire and stuff. It can get pretty crazy. Okay, so these are the halogens. This is actually what these halogens look like over here, the chlorine, bromine, and iodine. Ooh, they're so colorful. You would not want to breathe those in. That would be very bad. Okay. Notice that we don't really talk about the halogens after the iodine. Anybody know why? Okay. You're going to get this in a bit, but they start getting more metal-like. Okay? So they start going to so low in the periodic table, they get much more metallic in character. And so it ends up getting kind of weird.
Wait, so don't they use like iodine in medical practice?
They do,
Okay.
but not iodine in its gaseous form. Yeah. And interestingly enough, so did you know that iodine solutions over 2% are now actually a class 1 compound in the United States? Yeah. Which is funny because you can buy iodine solutions in 1% in the 44-gallon barrels, and you could just boil them for a little while and you'd have the 2%.
There's a whole lot more paperwork when you have 2%.
Yeah. It's like I tried to order it for a lab, and oh my goodness, the shit that came down on me. You would have thought I was like, we should make meth.
That's probably why you're locked.
Yeah, maybe. Which is why it actually got banned, by the way, because you can make meth with it.
Yeah.
Which option is in group 7A or group 17?
That's why we import it. Hey, I'm serious. It's so much easier.
Oh, yeah.
Just going through the legal process, even as our company. It's just.
Oh my God, yeah. Did you hear about the chemical orderer down in Texas that was working for the mafia? Or I should say the cartel they were actually working for.
Are flickers based on correctness or participation?
So clickers are mostly based off of participation, unless I start getting a lot of issues with people not really participating. There we go.
It's a habit.
Okay, it is fluorine. And if you looked up at the periodic table, that would have told you the answer, wouldn't it? So we look at group 17 on this periodic table. We trace down on that group, and that is F. There we go. By the way, the O here and the oxygen here actually kind of should have told you because I doubled it, right? And then the other one, which is sodium, is way over on the left side, isn't it? Yeah. Yeah. But anyways, that's the test taking strategy, by the way. You may want to sort of think about those things. Okay, so this is one place that's going to be a bit of a contentious issue, and if you look it up, it's kind of an interesting thing. So I'm going to tell you right now, your book is actually wrong for the metalloids, okay? Okay, we're going to talk about it first, and then we're going to talk about what your book has, and then we'll go through it. Okay, so if you look at a periodic table, many of the periodic tables don't really have a really nicely marked out diagonal line anymore. But if you look at it, starting at aluminum and boron, so if you look up at aluminum and boron, see that? There's a zigzag line that should go through like so. Everybody see that okay? Okay. Yeah. And I don't think you can really see it up on that periodic table there. And so what that is that line is the denominator that notes that on the left and bottom of that line are what's called the metals, right? And so they're going to have properties that are metallic, okay? And you all pretty much know these properties because metals are all around you. On the right side of that line is what's known as the nonmetals, okay? That's the top right side of that line. And basically, these nonmetals just have properties that are not metal-like, okay? They have very few of the metal properties. Literally called non-metal, right? They're things that are not metal. Okay. And then the stuff that has two sides that are connecting to that line are actually supposed to be the metalloids, okay? So your book actually says are located along the heavy zigzag line between the metals and the non-metals are the metalloids. But you can see even the where your book says that, its own line here has this one right here as not being a metalloid. Can everybody see that okay? So even within your book, it's contradictory right there on the same page. All right. So what's going on is these metalloids are basically stuff that's kind of metallic, kind of not metallic. Okay? It has a lot of metal-like properties, but not all of them. Okay? It's the stuff in between. Where we go, is it a metal or is it not a metal? Case could be argued either way. Okay? Now, if you actually look this up right now of these different elements here, and are they a metalloid? You will see there's two of these elements in here that are not metalloids right now. Okay? And this happens every few years. Basically, somebody comes up with a new test to try to denote metal versus non-metal, and it ends up grouping up new things into it, specifically usually the metalloids. Okay? So just know that this cutoff here, the stuff that's on that cutoff, they're not fully metal or fully non-metal, okay? They're in the transition between. Does that make sense? Okay. They're the gray of metal. Okay. I tried to make a pun, but it didn't work. All right. Now, most metals, what are some defining properties of metals? They are shiny solids, right? That a good description? So if you look at copper, you look at gold, you look at silver, these are all the what's called coinage metals. They're shiny metals. Specifically, those metals are not very reactive either. They're ductile. That means they can be shaped into wires. They are malleable. That means they can be hammered into flat sheets. They are good conductors of electricity and typically good conductors of heat as well. They're going to be melted at much higher temperatures than the non-metals typically are. And mostly they're solids at room temperature, the exception for this being mercury. Mercury is a liquid at room temperature. Mercury is one of the very few liquids at room temperature on the periodic table. So what is a nonmetal? Well, nonmetals are things like hydrogen, carbon, nitrogen, oxygen, chlorine, sulfur. Nonmetals are not especially shiny. They're not especially ductile, malleable. More often than not, they're poor conductors of heat electricity, typically have low melting points, low densities. Notice when I kept saying typically, usually on these. Basically, metals have almost all these properties almost all the time, right? And if we look at something like a non-metal, they will have very few of these properties, okay? Or none. Now, you can make arguments and try to argue things like, for example, diamonds are carbon. Diamonds are quite shiny. Diamonds actually have very good conductors of heat. They can't be hammered flat, exactly. If you take a hammer to a diamond, you actually break it. Did you know that? Yeah.
Well, the diamond will break that.
No. The diamond will break.
Really?
Oh, yeah. Oh, yeah. So they make what are called diamond windows for cells, for spectrometers, things to detect what something is. And if you take the top of one of those out, it's a chunk of steel about that big, and then it has a little diamond on top. And if you drop that, it'll actually break the diamond when it hits the concrete floor. Somebody actually did that in one of the labs I used to be in. And it is an $8,000 diamond chip because it has to be incredibly pure. And so it was quite a pricey fumble, right? And yeah, if you took a diamond and you got it clamped down in place on like a concrete floor or a piece of iron or something, yeah, you can actually hammer on it and break chips off. Yeah, diamonds are not especially strong. They're hard. They're very hard.
That's probably the hardest.
Theoretically, the hardest material of nature. Though we've actually found a few things that, depending on how you do the test, may be harder. Like in meteors and stuff. They're actually forms of diamond. So it's kind of cheating. But anyways, that's nonmetals. When we get to metalloids, they're really just kind of in the middle, okay? So they're going to have some of the metal properties, some of the non-metal properties. Better conductors of heat and electricity than most nonmetals, but typically not as good as a metal, okay? They're going to be semiconductors. If you're going to look for a semiconductor, more often than not, it would be found in the metalloids. Anybody know what a semiconductor is? Yeah, they're sometimes conductors under certain conditions, sometimes insulators under other conditions. They're used to make computers. That's how a computer works, actually. So it does the calculations, and the calculation actually makes it a conductor or not a conductor, and that tells you the answers. Yeah, that's very simplified, but overall, that's what's going on. And that's why silicon, by the way, is used as the semiconductor in a computer. Okay? Okay. Anyways, these are some different characteristics, some different examples. It's just what we had talked about right before. So of all your elements, about 20 are going to be essential for the well-being and survival of a human body. The 4 elements, oxygen, carbon, hydrogen, and nitrogen, actually make up 96% of our body mass. They are the vast majority of us. Why would that be? Why is that almost all of our mass?
We're a lot of water.
Yeah, partially it's because we're just a lot of water. We're big water bottles, right? Or squishy water mats. Okay? The other part of this is that those are the ones that are pretty common to find. Like, would you want to try to depend on finding platinum? You have to find 100 grams of platinum to be able to survive every day. Is that going to happen? No, you'd definitely be dead. There'd be very, very few humans, right? So again, it's just pure, these are common things to find. Okay? Now, if we look at the macro minerals we need considerably less of than the oxygen, carbon, hydrogen, nitrogen in our system. Again, these are one of the major components of the remaining 4%. Okay? But we need significantly more than the micro minerals. So these are going to be things like calcium, phosphorus, potassium, chlorine, sulfur, sodium, and magnesium. Yes, you do need sodium in your diet, in case you're wondering. Yes, if you did not have table salt at all in your diet, you would actually die. Okay?
I love salt.
Yeah, unfortunately in the U.S., it's really too easy to get your hands on, right? And it is something humans are engineered to love. Because it's actually supposed to be a difficult thing for you to get. Okay? Mm-hmm. Huh? Yeah, plants. Yeah, so typically you're actually going to get that in like plants and eggs. In fact, have you ever smelled a rotten egg? Yeah, that's actually sulfur you're smelling. So that's methyl sulfide is the smell of rotten eggs. And what's happening there is bacteria have gotten into it and started eating the egg, and they're emitting the sulfur as the methyl sulfide. Okay? And so typically we get these things, the phosphorus, sulfur, chlorines, ultimately from plants. And the plants typically are getting them from the soil. Now we may get them secondhand where like the bug ate the plant, the bug got ate by the chicken gave us the egg. But ultimately it traces back to the plant. Yeah. Does anybody know which came first, animals or plants?
Land.
Nope. Animals.
Compost.
By a lot. Yeah. By 100 million years. In the ocean.
Oh.
Yeah. Yeah. And plants didn't come quite a bit after. Yeah. So, kind of an interesting little thing. Plants are actually the more evolved, more recent, more DNA complex creatures. We are the less evolved, older cousins. Yeah. So, these things are going to be involved in things like the formation of bones and teeth. You may note of that as calcium, right? Maintenance of heart and blood vessels. Commonly, that's going to involve sodium, magnesium, etc. Muscle contractions. That's the magnesium, potassium. Potassium being a big one, right? That's why you have the Charlie horses. You don't eat bananas and stuff. Nerve impulses, acid-base balance of body fluids, and the regulation of cellular metabolism. These are just a few things. You need a fair amount of these in your diet, though not a huge amount. So the other essential elements, these are going to be called the micro minerals or trace elements because they're a very, very small amount of the weight. Okay? And these are going to be mostly transition elements. They'll mostly be in the period 4 along with silicon in period 3 and MO and I in period 5. They are actually present in the human body in amounts that are less than 100 milligrams. Okay? Which is pretty small, right? Considering we're talking about a whole human. Okay. Now, being small amounts and you not needing a lot of these, does that mean they are unimportant?
You would die without it.
Yeah, they're incredibly important. Anybody notice that microminerals, iron? You've probably all heard of not having enough iron, right? Yeah. And so, extremely important. Anybody hear of zinc recently? You know what one of the most effective treatments for COVID was? Zinc. Which is just wild, right? It was actually more effective than the drug designed to combat COVID. Copper is an incredibly important one. Nobody ever thinks that they need copper. Do you know where you get iodine in your diet? Okay, iodine's actually kind of hard to get in your diet. And these things are kind of the things that, if you hear about people starving in the United States of America, this is typically what they're talking about. It's that they're eating foods that don't give them the micro minerals they need, and they're not getting those, and so they're not healthy. Okay? Iodine typically shows up in your iodized salt in your diets. And so anyways, if you ever hear stuff about like food is becoming less healthy, etc., this is usually what they're talking about, okay? These micro minerals. Yeah. Mm-hmm.
Is it actually becoming more unhealthy, or is it just becoming more laden with the microchemicals?
No, they're lacking micro minerals now. Yeah. And so, and it is actually a lot of the foods now, because they're pretty heavily processed, they aren't contaminated with the micro minerals, but you need that contamination.
So in the process of cleaning them up to make sure they don't have viruses or other germs, or they aren't spoiled or rotten, we're inadvertently also removing all the little tiny things we need from them.
It's not for the process of viruses and germs and stuff. It's because what we're doing is we're making them in these huge batches, and we're quality controlling them. And because we're doing that, we have not been adding these micro minerals in, which is what, if we're going to continue doing that, we need to do. And that's not actually that hard to do. It's just like a decent nutritionist needs to actually get behind the scenes and go, you need to add micro minerals, right? And it hasn't been something that's been done. Also, there's some arguments that like soil depletion has started happening in the United States because we rotate crops. We don't rotate the correct crops where we're doing large-scale farming. And so these micro minerals are getting pulled out of the soil. And so like a head of lettuce has less micro minerals in it than it did 100 years ago.
Because you gotta rotate your fields to allow the nutrition to come back.
Partially you have to rotate your fields, but a lot of these micro minerals would not actually replenish. You'd have to let rain get at them for a long enough period of time. So we're probably going to end up in a state at some point in the next like couple decades where we have to add micro minerals to stuff, and we just have to do it ourselves. We're on that brink right now of like people can still get enough of these, but it's not easy. Okay. Anyways, it's a thing. Keep it in the back of your head. Me personally, I actually take a supplement that gives me all my micro minerals. I probably don't need it though, because I don't eat like pizza every day and stuff like that. So, but yeah. Anyways, this is right here is actually the different elements of your health, and some of the most important ones are denoted out right here. And so there's some pretty crazy stuff in here if you actually pay attention to it. Like many of these things, if you were to have too much of them, would actually, or the wrong species, would actually be poisonous. For example, many of you may have heard of chromium as a poisonous substance. And that's hexachromium, a chromium with a 6+ charge. Yeah. The chromium with the 3+ charge is a nutrient. And you need it. Weird, huh? Yeah. So atoms, all of the elements that are listed on the periodic table are going to be made up of atoms. An atom is going to be the smallest particle of an element that will retain the characteristics of that element. So if we zoomed in enough, we could see the atoms of aluminum, for example, right here. If we tried to subdivide those anymore, we would get stuff that doesn't have any of the properties of aluminum anymore. Okay? It would be something entirely different. Does anybody know what the next step down is?
They're subatomic.
Subatomic, yeah.
That's what like, protons, neutrons, electrons.
You got it. Protons, neutrons, and electrons. Okay. Dalton's atomic theory. The idea of atoms did not become scientific theory until 1808. So John Dalton, 1766 to 1844, actually developed an atomic theory proposing that atoms were responsible for the combinations of elements and compounds. Now, note that there is some debate that people propose things, similar ideas, but Dalton is the one that gave something that could actually be tested, okay? And went through and proposed principles that would have to have. Now, all matter is made up of tiny particles called atoms. So this is Dalton's atomic theory. All atoms of a given element are identical to one another and different from atoms of other elements. So if I have a carbon from a human, a carbon from a plant, and a carbon from gasoline, are those different? No, carbon is carbon, no matter what. Okay? So an atom of two or more different elements combine to form compounds. A particular compound is always made up of the same kinds of atoms and the same number of each kind of atom. And so if I have carbon dioxide, I'm breathing out carbon dioxide right now at you when I'm talking to you, aren't I? That's how I'm talking. The plants, they give off carbon dioxide out there. The rainforest gives out carbon dioxide. The tailpipe of my car gives out carbon dioxide. Are those different? Nope, they're the same thing. So, number 4, a chemical reaction is going to involve the rearrangement, separation, or combination of atoms. Atoms are never created or destroyed in a chemical reaction. Now, we know this same statement, but it's a much broader statement now, right? Mass is neither created nor destroyed, right? Yeah. It's only changed. So, subatomic particles. By the end of the 1800s, experiments with electricity actually showed that atoms were composed of tiny particles, and these were called subatomic particles. Literally, sub, smaller than atoms, right? These will include your protons, neutrons, and electrons. Does anybody know what electricity is?
It's the charge.
It is moving electrons. So all electricity ever was electrons moving around. Okay? Kind of like water, right? Moving water, moving electrons. Okay? Water makes a very good analogy for electricity, by the way. So it is shown that subatomic particles of an atom actually have a charge. Specifically, electrons are what charge? Negative. You got it. Anybody know the positive one? Protons. Yep. Very good. So the electrical charges, these can be positive or negative. 2 positive charges are going to repel each other. 2 negative charges will repel each other. And a positive and negative charge will attract, right? Okay, everybody's familiar with this concept? Okay. I'll tell you what, you go on Amazon, you can find product descriptions all day that say the reverse. It is just wild to me that anybody could write a product description, think they're going to sell stuff on Amazon, and actually sell stuff on Amazon and not know positive or negative and a negative repel. I'll buy a mice repellent. The particles of the repellent are negative and the rodents are negative, so they they attract each other. What in the world? So, 1897, J.J. Thomson discovered that cathode rays were streams of small negatively charged particles. Eventually, these were called electrons. These were proposed. J.J. Thomson actually proposed this model of the atom, which is the plum pudding model. Okay, Who here has actually seen plum pudding? Or does that make any sense for? Okay. Who here has seen some sort of matrix of either pudding or jello with little pieces of fruit in it? Or maybe cake?
I'm thinking of those 80s Slim Gelatin cake ones.
Yeah, yeah, it could be that. Or it could be,
Think like a fruit cake.
Yeah.
It's all like one that didn't have like the powder rings.
or raisin pudding. Wow, your Southern card may have just gotten removed.
I'm not from here.
I'm not either. That's fair. Anyways, you can at least imagine the idea, right? Okay. Anyways, this is they make pudding with little plums in them. This is plum pudding model. It has a matrix, which is the positive or pudding, and then the little pieces in it would be the electrons, i.e. the plum. Okay? Okay. And this would give you an overall balanced charge on your atoms, right? And we know that has to be true. The atoms actually have to be neutral overall, okay? Or else atoms would always repel each other or attract each other, right? They don't.
How did you get to the plum pudding method?
That's just what came to him. I imagine that he ate plum pudding as like, oh, if you suspended the negatives and a positive, okay. Yeah. And the other thing that he kind of knew that the positive stuff was heavier and had to take up more space, but we'll talk about it. It wasn't right anyways.
No, not at all.
No. So in 1911, Ernest Rutherford worked with J.J. Thomson and developed a new structure for the atom based on Rutherford's gold foil experiments. I mean, honestly, don't take that badly for J.J. Thomson. Like, he did what you're supposed to do in science, right? Made an observation, came up with a theory, plum pudding model, that he could test. And then what did he do? Tested it. Okay? And it was wrong, but to get to the correct answer, you have to go through the wrong ones, right? So, like, yeah. And that's actually what this is supposed to demonstrate. This is actually an actual scientific pathway, right? That we're going through. This is the scientific method we're going through right now. Okay? And demonstrating a well-done scientific method that actually got a very, very well-supported theory at the end through this process, right? Yeah. So, like, it's actually a really great story. Okay, so what we did to go ahead and test this is we did the gold foil experiment. And so over here you have a lead container, and in that lead container you have a radioactive substance. Okay? As far as I remember, this was actually emitting electrons, I believe, out of this. We'll talk about what that is in a radioactive substance later. But it was emitting little, small, fast-moving, negatively charged particles. Okay? Okay, and so what we saw when it hit the gold foil, if this was the plum pudding model, what would happen to these electrons when they hit it? Yeah, they'd get stuck, right? Maybe a few would come through, but most of them would get stuck. And the few that came through, would they get deflected easily? Not particularly, right? Yeah, you wouldn't expect a lot of deflection happening. But what actually happened is the majority of those particles actually went through. And then the other ones got deflected, and some of them got deflected by just a little bit, some of them got deflected by a lot, and some of them actually bounced back at you. Okay? And so we look at this and we go, by the way, this right here, see this stuff right here? That's just film, like you'd use in one of the old cameras. Yeah, they just took a sheet of roll of film and went like this. It's a pretty big roll of film, but yeah. And that's so they could record these particles getting deflected or going through or what they're doing, because it would have made little dots on the film. Okay? Okay, and so if we start thinking about this, well, okay, so we have mostly empty space, don't we? we know we have a negatively charged particle and a positively charged particle in there, don't we? Okay? And so if the negatively charged particles are in here, they have to be very small, they're very light, they're moving around all the time. So they have to be sort of in a orbitals or clouds or something, right? And the middle part has to be positively charged, and it has to be pretty heavy. Anybody know why it would have to be pretty heavy? Okay. So you spray water at your screen door, what happens? The water, some of it goes through, right? Some of it gets deflected. Some of it deflects back at you, doesn't it? Okay. Why does that happen? Well, your screen door doesn't move, does it? No. So what would happen, on the other hand, if I sprayed water at a bunch of cans?
Cans are good because they move and fall back.
Yeah, the cans would fly off, right? Okay. What if I spray water at a 44-pound drum? Doesn't really move, does it? Yeah. And so if they're heavy enough, they're not going to get thrown off, right? If they're too light, they'd actually would have gotten thrown with it, right? And you would have seen stuff popping all over the place. Yeah. And so, yeah, we got quite a few details from that experiment, didn't we? Good experiment. All right. Pretty cool. So from that gold foil experiment, the Rutherford determined that atoms contain a small positively charged region in the center. We called that a nucleus. If this nucleus was really big, what would have happened here? Would have we gotten much of the beam coming straight through? No, the majority would have gotten deflected, right? Yeah. So that's called our nucleus. Region of space is then has negatively charged electrons in it, and this is surrounding the nucleus. And we know that because there isn't something else to hold on to these electrons. Like, if you had a non-round space around it holding on to these, they would have been flying off all the time, right? Okay. So an atom consists of a nucleus. It contains protons and neutrons. I'm going to go ahead and skip the finding neutrons, and I'm skipping quite a bit of the figuring out what an electron is. But if you're interested in that stuff, let me know. We can talk sometime. Okay? But that's too much for this course. And then what we have is we have empty space, mostly empty space, and that has the electrons in it. Now, if we were to call this space that has the electrons, this first level of space that has the electrons, a football field in size, how big would the nucleus be?
2 yards.
A tennis ball. So every single model of a atom you have seen in any book, any show, anything, always has to be wrong. Because you wouldn't be able to see the nucleus or electrons if you could see everything else. Okay? Automatically, to make it visible to you, it's always way wrong. Okay? If we actually printed off an atom, we'd put this circle around the orbital here, and then you'd need a microscope to see the nucleus. Okay? All right. And so this right here is the nucleus. It has neutrons and protons in it, and around this nucleus there are electrons. They don't actually circle it in orbitals, which is what you probably have seen most. They actually pop in and out of existence all over the place. And so we just go, we can find them in this area 90% of the time and just draw the area out. Okay? Which is those orbitals you've seen before. So let's talk about mass. We have the atomic mass unit. This is going to be the mass of the atom. It's going to be due to the protons and neutrons in the nucleus. The electrons have a much, much smaller mass. Does anybody know about what that ratio is? The electrons are about 10,000 times less in mass. Okay? So about 10,000 electrons would give you the mass of a proton. Okay?
So how many protons and neutrons are in the nucleus? That's what the atomic mass is?
It is. Yep. Number of protons and neutrons. So again, we have labeled this atomic mass units, AMU. This is the mass that's equal to 1/12 of the mass of a carbon atom that has 6 protons and 6 neutrons. Now, you may be going, Dr. Clausen, protons and neutrons probably have different masses, don't they? And you are absolutely right. And unfortunately, that is what's going on down here. So, we typically will go ahead and just say a proton has 1 AMU, but if you were to actually measure that out, protons typically would have about 1.007 AMUs. Okay? We just round that off and call it good. Neutrons have 1 AMU again. We typically just use 1 AMU whenever we're doing these things, but if you were to actually take that mass, it's 1.008. Okay? Anybody notice that the neutron, the neutral one, is a little bit larger in mass? Okay, so right here we have electrons mass that is 0.00055 AMU. Okay? If you were to take the difference between these two, it is about the mass of a electron. Yeah, the extra mass on a neutron is the electron. Okay? Okay, how's my time, by the way?
You got 4 minutes left in this.
3-4 minutes? Okay. Let's go ahead and sum this up real quick. Here we have protons, neutrons, and electrons. The symbol for a proton, correctly done, is P+. You can abbreviate that to just P. Okay? N0 is neutrons, or N for neutron. An electron is E to a negative. The charge of a proton, hey folks, please don't try to talk over me. It's getting very difficult, and I don't want to have to yell as loud as I have to. Okay? My voice goes out. So, a charge of a proton is a 1 plus. Does anybody know why it would be a 1 before the plus? The definition of a positive charge is a proton. So you literally have 1 positive, 2 positives, 3 positives, rather than being +1, +2. Yeah. Neutrons have a charge of 0. Electrons have a -1 charge. These are the masses. These are the location. Anybody have any questions? Fantastic. We'll start up on here next time.